Welcome Math 20-2 to your first lesson in mathematical reasoning. In today's lesson, we're going to look at inductive reasoning, conjectures, and counterexamples. So it's just kind of an introduction, letting us know what everything is. I'm going to start with this exploratory part 2. So here we have all these shapes and the patterns. And now part A says, continue his third sketch. I look at this. When I look from this sketch to this sketch, we add 2 on the corners of this trapezoid or trapezium. Look at this one here, we add 2 more. Same with this one. There's 2 more added, so 2 more to each one. So here I'm going to have to add 2 more of these to this, to each corner. I'm going to have to bear with my art. It's pretty horrible. There we go. So those are all of mine. This one's touching. We'll just pretend it's touching, okay? There we go. So now it says, Bruno wondered how many trapezoids would have to be added in the 5th sketch. So we're going to complete this table to figure it out. So there's 2 added in the first. The second one we have 1, 2, 3, 4. 4 is added. The third one we have 1, 2, 3, 4, 5, 6, 7, 8. 8's added. Look what's happened. The fourth one, we'd have 2 for this one, 2 for this one. So there's 2 being added for each one. Okay, so I'm going to say 16. The next one's going to be 32. Then we're going to have 64. Okay, now what can we conclude? The number of what can we conclude about the number of trapezoids added in the 10th sketch? Well, this here is the same as 2 to the 1. This is 2 squared. This is 2 to the 3. This is 2 to the 4, 2 to the 5. I'm going to say it's 2 to the 10. Trapezoids will be added, which is the same thing as, put in my trusty calculator, 2 to the power of 10 is 1024. Okay? And that's it. So now we could go over some definitions. What is inductive reasoning? So inductive reasoning is a type of reasoning on which we arrive at a conclusion or a generalization, educated guess based on experiences. Okay, so it's kind of like you have an experiment, we're doing a lab, and then based off of what we find in the lab, we come up with a conclusion, okay, or a conjecture, which is inductive reasoning. So if so many things happen, we come up with a conjecture or a conclusion, which is inductive reasoning. So what is a conjecture? A conjecture is the conclusion you come up through inductive reasoning. Okay? So the use of tables help us determine conjectures. So such as the one we did just before. Okay? So conjectures also may or may not be true. So sometimes we could disprove a conjecture. So it's kind of like it's there, but it's not always 100% true. Okay? So let's just look at B here, because we didn't do this A. You could do this one here and look at it yourself. I just didn't have a protractor. So let's look at B. It says, Bruno used inductive reasoning to arrive at a conjecture from part 2 in the investigation. Okay? So how did he use? Well, he looked at the number of new trapezoids was doubled each time. So in this table, we look at this, the number of new trapezoids was doubled each time. So the first one was 2. The second one was 2 times 2. The next one was 2 times 2 times 2. And then the fourth one is going to be 2 times 2 times 2 times 2. So it was doubled each time. Therefore, Bruno could extend the pattern. So we could guess what the 5th and 6th one. The 10th one would be 2 times 2 times 2, 10 times. Okay? So that is exactly what he did. That was his inductive reasoning. Okay? So he noticed the number of trapezoids doubling. Okay? Each time. Okay, then he extended the pattern. This is kind of like how we had those tables in the unit before. Remember when we tried to find linear scale factors to area scale factors and then to volume scale factors? We had a table and we looked at one side then the other, the linear compared to area, linear compared to volume. And then we were able to make a conjecture based off of inductive reasoning to find a pattern. And we will be doing this a couple more times, okay? So, the next part here is we're going to look at counterexamples. So counterexamples could show that a conjecture is not true. So here we have Katie and Perry were given the following patterns by their teacher. Okay? Katie's task was to make a conclusion based on only the number patterns shown with no further investigation. Perry's task was to see if Katie's conjecture was correct or not. So Katie made the following conclusion. She said, when an even number is squared, okay, when an even number is squared and 1 is added, the result is a prime number. So we add 1, get a prime. 4 squared plus 1 is 17. So she kept on going on. So Katie's conclusion is a conjecture. Sure, okay, based on inductive reasoning. Okay, now Perry investigates Katie's conjecture further by using even numbers not shown. She correctly stated that Katie's conjecture is false. Determine a counterexample. So I have these here. Well, let's just try one I'll give you. If I have 8 squared plus 1, well, is that going to be prime? I know 8 squared is 64. When I add 1, that's going to give me a total of 65. Okay? And with 65 can be divided by 5. There is 1. All right? Okay, let's take a look at the next one here. And also another one could be 12 squared. Let's look at 12 squared, which is equal to 144 plus 1, which is equal to 145. So there's a second one. You might come up with more. So the next one says, Mick and Sue were discussing what conjecture could be made regarding prime numbers in the pattern shown. Okay, so we're looking at these in the pattern shown. They both agreed to the following conjecture. The sum of 2 prime numbers is an even number. Okay? So the sum of 2 prime numbers is an even number. Now, let's take a look. We have 2 primes. Well, that's always an even number. Okay? Now, it says revise their conjecture so it holds true for prime numbers. Okay? Well, is 2 a prime number? We're missing 1. 2 plus 3 is equal to 5. There's one that doesn't work. That would be a counterexample. So provide a counterexample. 2 plus 3 or 2 plus 7 is equal to 5. Or 2 plus 7 is equal to 9 because 2 is prime. So now we have to revise the conjecture. So how do we revise it? I am going to say, well, we have the sum, the sum of 2 prime numbers. I'm going to put 2 here like this. Numbers. I'm going to say excluding 2. Comma. Is an even number. Okay? That's what I'm going to say. Now, make a conjecture based on the number pattern if the condition prime number was removed. So, the condition prime number was removed. Well, if I'm looking at this, these are all odd. So then maybe I could look at it a bit different. So the sum of two odd numbers is an even number. Okay? So there we go. All right. Here we go. Let's take a look at class example 4. So here it says, he noticed that in all the patterns, so Jerome investigated the following. He noticed that in all the patterns, 3 consecutive integers were being added. Okay, so we have 3 consecutive integers being added. Write 2 or more patterns showing the sum of 3 consecutive integers. All right, well, let's try 6 plus 7 plus 8 plus 6 plus 7 plus 8. So it's 15. It's going to give me 21. Okay? Let's try another one. I'm going to try 2, 3, 4. 2 plus 3 plus 4. 7, which is 9. Okay? And just wait, write 2 more. So there, I have 2 more. Okay? Now it says, use inductive reasoning to make a conjecture based on the 3 consecutive integers. When I look at all of these, what's this divided by? This is divided by 3. This can be 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 divided by 3. So then I could say the sum, by deductive reasoning, my conjecture could be the sum of 3 consecutive integers is equal to a multiple of 3. Now, we might be able to make this even better. If I look at this divided by 3 gives me 7. This divided by 3 gives me 3. This divided by 3 gives me 2. This gives me 6. This gives me -5. This gives me -11. So I look at that, it could be even better. So the sum of consecutive integers is equal to the middle number multiplied by 3. By 3. Okay? Now, here's a little note, and it's kind of letting you know this, if we do when we do inductive reasoning, it's not always true. Okay? You're coming to a conclusion. In order to prove it, we do something called deductive reasoning to prove something. And we're going to learn about that later on. So now, here's our last question. It says, draw and graph the equation y equals to x. Okay? Using her graphing calculator and use this window. After observing the screen, she made a conjecture y equals x to the power of x has the domain of this. Show that her conjecture is not true by providing a counterexample. Okay, so we want to know, we says is an element of all real numbers. So why don't I try a negative number? Okay, so let's try this. So I'm going to say if x is equal to -1. So we're going to have y is equal to, we have -1 to the power of -1. Which is the same as, so we say it must be greater than 0. -1 all over, well, this means we have to flip it, sorry, we take the reciprocal. 1 over -1 to the power of 1, which gives me -1. So that is less than 0, so that's not true. Another one could be y is equal to, let's try, we have x is equal to -2, so that's -2 to the -2. Okay, so I go 1 over -2 squared, which is the same as 1 over 4. But this one works. So it's only this one. It's not all negative. It's only if I use that one. Thus, -1 could be in the domain, and it does not work. Okay? But if I did -3, that one would probably work, wouldn't it? because that would give me negative 3 to the 3, which is 1 over negative 27, which is still below. So that's interesting. So we could say for all positive integers, if they use natural numbers here, or all positive integers, that's true, or something like that, okay? It's not true for anything less than 1, when x is less than 1, all right? So there we go. So you could actually rearrange this to make it more true. So hopefully you understood this. Good luck as we meet tomorrow.